Okay, so it is unfortunate that other organizers are not here to introduce me, but maybe you have seen me around. So I am Rishi Khatri, and I will try to cover a little bit of, tell you a little bit more about CMB than Professor Dmitry Pogosyan already taught you. So he taught you about Sachs-Wolf effect and a little bit about acoustic oscillations. So just to set the conventions, so the convention I am using are actually same as the Dodelson's book. So there's a small difference with respect to what Professor Pogosyan was using. So in particular, phi, my phi is his psi and my psi is his phi, and there's a difference in minus sign, just to keep you on your toes. But it is not very important for the physics that we will be discussing. And we will be talking about CMB temperature anisotropies. So we have delta T over T, I will denote by theta. And these are the Fourier modes. So you take the Fourier transform. So you have a temperature field, you take a Fourier transform, and then the Fourier transform, again, you decompose into the spherical harmonics or into these multiples using Legendre polynomials. I think you already, Dimitri already covered all this. Mu is k dot over n is the direction of propagation of photons. K is the direction of the wave number. Okay, so with this in mind, so you already have learned about scalar vector tensor decomposition and the scalar perturbation equations. So let us start with the perturbation equations for the CMB temperature anisotropies, CMB and baryon system, the coupled CMB baryon system. So all we need is actually the three equations. First is the equation for the multiple theta 0 monopole. Again, this equation should already be there from Dimitri's lectures. So tau dot is the differential Thomson optical depth, and the dot represents the derivative with respect to the conformal time here. Vb is the baryon velocity. These factors of I come actually just because of our convention that I am following for these multiples. There's nothing deep about these factors of I. Okay, so these are the equations which describe this coupled baryon photon fluid that exists before recombination. We want to study the structure of these equations and what they tell us about what is the dynamics that is going on in this tightly coupled baryon photon plasma. So there are factors of R here. R is just the ratio of baryon energy density, average baryon energy density to the photon energy density times a factor of 3/4. So R goes to 0 means that the baryon density is completely negligible. And large value of R means that the radiation density is negligible compared to the baryon energy density. Right, and these over dots represent the derivatives with respect to the conformal time. Okay. So this much you should already know if you are paying attention in Professor Pogosyan's class. So now we want to study these equations. So these are general equations, they are valid always. We want to study them in the tight coupling limit. So in tight coupling limit, the baryons and baryons and photons are moving together, which means that this term, this Thomson optical depth is very, very high, which means that this term should be very, very small if all of this has to remain finite. Which means that theta 1 is very, very close to, so theta 1 you can think of as the photon velocity. So photon and baryons are moving together, so their velocities are same, they are moving together. What we can do is, if we look at this equation here, so this second term is very, very small, because when Thomson optical depth is very, very high, this term is suppressed. Which means that in this term, we can approximate VB by θ1. And then this will be correct up to first order in 1 over tau dot dot. Right? The difference between these two is of order 1 over tau dot, 1 of the Thomson optical depth. And if we want equations which are correct to first order in 1 over tau dot, we can just substitute θ1 over VB here, and the corrections will be second order. So once we do that, we get VB is approximately 3I θ1 over plus R over tau dot. Right, so we have actually a solution for VB. So once you substitute VB in these two equations, we now have two equations for two variables, θ0 and θ1. In principle, we should also have equations for psi and phi, right? They should come from Einstein's equations. But we will make simple approximations, and we will not need, we will try to solve just these two equations, to treat them as psi and phi as some external potentials, and try to solve these two equations just as equations for two unknowns, two equations for two unknowns. So once we have this, actually we have two first order differential equations which are coupled together. We can actually convert them into a single second order equation for θ0. This is just some algebra which I will not go through in detail. But you can see how this will happen. You just take a time derivative of this equation, and you will need a θ1 dot here. So θ1 dot you can substitute from here. So then you have an equation which only have time derivatives of θ0 and θ1. It does not have time derivatives of θ1. Then θ1 you can substitute again using this equation. Right. So first equation, let me call this 1. Let's call it 2 with or let me call this one 2. So you take time derivative of equation 1, then you substitute θ1 dot from 2 into 1. So let us call this 3. When you take time derivative, to substitute θ1 dot from 2 into 3. Then you have an equation for this, gives you equation which has time derivatives of θ0, but no time derivative of θ1. And then θ1 we can substitute from here. So now we can solve this equation actually for θ1 in terms of θ0 dot and phi, and we substitute there, and we get a single equation for just θ0. So you can do this algebra in your privacy of your rooms. So I will just give you the final answer. We have a second order equation for this monopole θ0. Maybe let me write it here. Actually, this is the important equation which we will be studying in almost half of the lecture. Let me write it here. We have gathered all the metric perturbations on the one side and all the temperature perturbations on the other side. And this I will just call f, which is a function of psi, phi, time, r. This is the oscillator equation with a damping term. This is a pressure term. Cs is the sound speed. So Cs square is sorry. Is 3, 1 plus r. So when there are no baryons, if you have a pure radiation fluid, the sound speed is 1/3. But the baryons add some mass to the fluid, it decreases the sound speed by a factor of 1 plus r. Right? And this is the force term or driving term. Okay. So let us first ignore some of the terms, try to find the simplest solution. So if we ignore the damping term, this will actually just suppress the amplitude of the oscillations by a little bit. Driving term will just driving force. But even without this, we ignore the force term, all the gravity, and ignore the damping, that is the presence of baryons. So in the limit of, you ignore gravity and r goes to 0, there are no baryons, it is a pure radiation fluid, tightly coupled radiation fluid. And this becomes a very simple equation. It is just theta 0 dot dot, that's k square cs square. Right? And you know what is the solution for this. This is just the oscillator. The solutions are plane waves. What does this mean? What does the solutions mean? So the solutions will be something like, so in the limit that we have taken, it will be cosine k eta over √3. But in more general, when we cannot ignore baryons, then sound speed is not exactly 1 over square root of 3. We have this factor of r here. In that case, the more general, you can solve it in more general case also, and then it is Rs, where Rs is something known as the sound horizon. So this is the solution if you don't approximate Cs by, if you keep the Cs, this full thing, then the solution we get is this. But in the limit, the Cs is just 1 over square root of 3, we get this. So what does this mean? So remember that theta is already, so this theta multiples, theta 0, we have already taken the Fourier transform of our real space field. We had a real space field, we decomposed into plane waves. And so you have some real space temperature perturbations. You took a Fourier transform, decompose them into plane waves. Right? And what we are solving for is the transfer function of for these amplitudes of the plane waves. Right? So this was initially a Gaussian random field, and these amplitudes we write in terms of a transfer functions, which in case are these multiples, theta 0, theta 1, times the initial conditions. Some initial curvature perturbation, let us call them some zeta or something. So all the direction dependence of k goes into this initial conditions. Theta 0 just depends on the magnitudes of k. Right? And these were the equations, the perturbation equations that Dmitry Pogosyan had derived. We already decomposed into plane waves. So what are these oscillations of? Oscillations are for the amplitudes of these plane waves. So the amplitude of the plane waves is oscillating. So let us try to plot this. So let us take one k mode, one plane wave. Right? It is something like this. This wavelength, one wavelength is lambda is 2 pi over k. Right? This is the real space now. So I put one wave in real space. So this is the x direction, and this is the amplitude that we are solving for. This. You start with the amplitude. So amplitude is this. So you start with the amplitude, which is A. As the time passes, the amplitude decreases. So at about k eta over root 3 equal to, let us say, pi by 4, the amplitude of the wave has decreased. It has become this. Right? If you go to pi by 2, it has become 0. Then at 3 pi by 4, it reverses direction. Then you go to pi by 2, which I don't have space here for. You just is the inverse of this. Right? So if you look at this, so this is basically just like a string motion. If you pluck a string, it is oscillating. Right? So these are standing waves. In real space, we have standing waves. So these are standing sound waves. The amplitude is oscillating. So we have solution for theta 0. We can actually use the first equation to write down the solution for theta 1. And theta 1 is, okay, cannot cross here. I have to go back. So theta 1 is just the time derivative of theta 0. So you take time derivative of cosine, you get a sine, which means that the, let me plot them here. So theta 1 will be actually 90-degree phase shifted by this. So same wavelength, at time t equal to 0, it is actually 0. Because this amplitude is maximum. Pi by 2 phase shift gives you 0. Then it starts to oscillate. And right, so then it will start to oscillate. As this amplitude decreases, the amplitude of theta 1 increases. And when this is 0, this is there's a 20-degree, pi by 2 degree phase shift between theta 0 and theta 1. This is just like with the sound waves that you expect in your classical fluid mechanics. You have these pressure waves, and you have internal energy and kinetic energy, which oscillate 90-degree out of phase. So the total energy is conserved. Right? So in sound waves, the theta 0 is like the internal energy of the photons, and theta 1 is the motion of photon fluid, is the dipole. So it is like the kinetic energy of this photon fluid, and the this acoustic motions just convert internal energy into kinetic energy and back and forth. The total energy is always conserved. And so any perturbation, initial perturbation, it starts oscillating as soon as it enters horizon, as soon as k eta is some non-zero value. Okay. We are studying sound waves in the universe without any gravity, which means that gravity is not essential to create the sound wave. They exist irrespective of the gravity. Gravity just provides the driving force. So what will gravity do? So now let us introduce some dark matter. Again, make some simple approximation. Let us assume that potentials are almost constant, so we can ignore these terms. Right? Just to simplify the equations. And psi is a constant, which means that you have a constant driving term. You have a constant force for each k mode that is acting on the oscillator. So we can solve these equations without the damping term. But now we include the source term. And again, this is easy to solve. The solution is same. For the solution, you add a constant term. So what the constant driving force does is, it just shifts the zero of the oscillations. That is all it does. The solution is, you solve this equation, the solution is theta 0 plus psi at time t equal to 0. This is the initial amplitude, and it is oscillating with, again, the same We do not have any baryons, so we don't need the sound horizon. We can use k eta over root 3. So this is the same solution as before. With a different amplitude. There are two differences. There's a different amplitude plus there is a constant offset. The cosine wave we just offset by a constant. We just have shifted the zero of the gravity has just shifted the zero of these oscillations. So for the adiabatic initial conditions, we have at time t equal to 0, let us say theta 0 is some constant a, and this is equal to minus psi by 2, right, at eta equal to 0, which is equal to, for adiabatic conditions, if psi is coming from dark matter, it is 1/3 of the dark matter density. Right, so in terms of this amplitude A, what this becomes is minus A so let us see, I think we will not need this. Let us see what this looks like. So now I will not plot in real space that I was plotting here. I will just plot this solution, this cosine solution, just the solution for the amplitude. So x-axis is now k eta, right? So our initial solution was for theta 0. So if a is a positive number, then that solution was something like this. For any particular k mode as a function of time, the amplitude is oscillating. But now, so gravity has done two things. It has actually introduced a phase shift also. Because now this becomes minus a. So this is f equal to 0 or f equal to constant. What we get is actually not this. So now remember that a positive means we have positive dark matter density. I erase that, so here. So a positive means positive dark matter density. So for positive dark matter density, now the solution actually becomes this. What has happened is that actually the gravity is much more stronger than the pressure, and it actually forces the first oscillation to actually fall into the gravitational potential wells. So dark matter density is positive somewhere here. So the first oscillation, as soon as the perturbation enters horizon, the photons and baryons, they fall into the gravitational potential well. So the first maxima is not the, for the starting with a positive value of initial amplitude, is not the minima for overdensity. Dark matter overdensity, actually it is not a underdensity but a overdensity, because everything is falling into the overdensities. So this is one thing that has happened, and then we have to add a constant offset, minus 2a. So minus 2a means that this thing will actually come somewhere here. So 0 instead of here will be somewhere here. Right? So this is a. So we subtract, okay, let me plot it here. So the oscillations are actually now happening here. So gravity has added a offset. Is that right? I think it is. Oh, sorry, I think it should be plus 2a. I think there is a sign difference here. Gravity has caused this. But now, what we observe is actually not theta. Because the photons that will, suppose this happens at last scattering surface, we will see photons from here, some overdensity, which are coming at a very high temperature. But photons which are coming from a high density, they will also suffer gravitational redshift. So the observable is not theta 0, but observable is actually, so it's just like the Sachs-Wolf effect. What we observe is actually theta 0 plus psi. This is the actual observable. So the theta 0 plus psi, so this is basically exactly cancelling the offset. So the gravitational redshift and offset exactly cancel each other. So what we will observe, so final observable in again zero baryon universe where you have only dark matter will be just this. The original oscillations and all peaks have the same amplitude. Without baryons, there is no asymmetry in the odd even peaks. The gravitational redshift and offset have exactly cancelled each other. Okay. I think we are doing pretty good on time. So now let us add a little bit of baryons. Okay, before I go further, did Dimitri tell you about how to go from these transfer functions to CLs? Anyone? You remember? Usually, actually, it is very simple. So we are doing all this in three-dimensional space, right? We are working with Fourier modes. But we observe CMB on the sphere, and we decompose them into spherical harmonics. So to go from, so what we see is, so you have some waves, right? You have modes in the early universe, a kind of recombination. And what we see is actually a spherical cut, a spherical projection of this three-dimensional oscillating plasma. And I will just give you the answer that, so the CLs are actually just these transfer functions. So in this case, this theta 0 plus psi square. And the projection, this three-dimensional to two-dimensional projection, it is done with Bessel functions. So JLKR, where R is the distance from us to the last scattering surface. And you integrate over the Fourier modes. So you project, so that is all there is from going from what I am talking about to the CLs that you see in the Planck papers. It is just the projection from three-dimensional space to a two-dimensional spherical surface, which is done with these Bessel functions. But all the features remain same. So all the features from K space, they exactly go into the L space. So here what we will observe actually, if you look at CLs, then CLs will be actually something like this. So you will have constant peaks, right? All peaks will have the same amplitude. And this spectrum will just go on and on. So now let us add baryons to that. Let us see. So to add baryons, actually, it is slightly easier to see what baryons are doing if we write the equation in slightly different form. So this is our main equation that we are trying to understand, which has all the terms. We can actually, so these phi terms appear just like these theta terms. You have a theta dot dot term, which is exactly like this phi dot dot term, and the coefficients of phi dot term are also same as this theta dot term. So we can bring the phi dot terms on the left-hand side and write equation for theta plus phi. So we can actually write this equation a little bit different form. We can write it as This is just the operator which is acting on theta 0. Right, and this is equal to right, minus psi times 1 plus r. So now the time derivatives of phi have disappeared on the left-hand side. Okay, so now in the metric conventions that I am using, for adiabatic initial conditions and no anisotropic stress, psi equals minus phi. Right, if you take the Newtonian limit, then there's no difference between psi and phi. So this I can actually write as just equation for in terms of phi. Now again, let us ignore the damping term. Right? And I also assume that these potentials are constant. Again, we can solve this equation. This is again oscillator equation, but with a forcing term. But because of the presence of baryons, the driving force has an extra term. And so the balance between the pressure and gravity is now disrupted. So here the pressure term is same, but the driving force has now an extra 1 plus r factor. So the solution to this equation is theta 0 plus phi equals some amplitude, some initial amplitude. Let us call it b. So again, you have now I will use this sound horizon because baryons are not zero. Sorry. Yeah, so 3 I have absorbed into this CS square. So there was a factor of 1 plus r which was coming from here. Yeah, there should be probably, yeah, maybe I missed factor of 3. Yeah, you are right. Thanks. Sorry? Did I miss the? Oh, yes, thank you. There is a, no, a dot over a is not missed. I have actually absorbed the time derivative into r. So I am writing this r dot now. So if you expand this, you will again get the same thing. Okay, again, this is a forced oscillator. We are assuming that potentials are constant. A forced oscillator equation. We are just oscillating term plus a offset. And the offset now is phi. So this is phi 2 plus r instead of minus psi. But again, we want our observable. Our observable was theta 0 plus psi. So first, let us say what will be the initial conditions. So when time is 0, this right-hand side should be equal to the value of theta plus phi at time t equal to 0, right? So the initial conditions give you the right hand, let us see. So initial conditions will give you that theta 0 plus phi at time equal to 0 equals b plus phi 2 plus r at time 0. So you solve this for b, you get some amplitude b here. It's just a function of theta 0 plus phi at time equal to 0, some combination. So this is again, so the amplitude is different, which means that the amplitude of oscillations has changed because of the presence of baryons. But more importantly, the offset has changed. So we write terms of psi. So this solution for, so theta 0, so let me write it here. Theta 0 plus psi is actually, psi is minus phi, which means it is this equation minus 2 phi. Right? So it is theta 0 plus phi minus 2 phi, which gives you theta 0 minus phi 1 plus r at time t equal to 0. That is what you get from solving this. We have some oscillations with some amplitude, which is different because of the presence of baryons. Minus, but now, so earlier when we calculated theta 0 plus psi, the driving force were vanished, right? This addition of psi exactly cancelled the offset due to driving force. But now the cancellation is not exact. We have actually a small driving force left, a small offset left. So in this, our observable theta 0 plus psi is the oscillations, but with a small offset, which depends on the amount of baryons that are present. So the solution now will be, we can remove this. So we had this solution earlier with no baryons, but now we offset by a factor psi r. So this is not the full offset that we were getting earlier. So small offset will, what it will do, it will do like this. So when you square this to calculate the power spectrum, so when you square this to get the power spectrum, you will get a asymmetry. So the power spectrum will go, wait. This is starting from a cosine, it is starting from here, right? So the power spectrum will be, first peak will be higher than you would expect in the absence of baryons. Second peak is smaller, third peak is again larger. You get a asymmetry between this odd and even peaks. Again, so additional things can, you can do a lot of things actually with just with this simple equation in solving it in different limits. You can do many different things. One interesting thing is, if you substitute the first term here, I will not go into this in detail. This is actually a very strong argument against modification of gravity. As an explanation for dark matter. So suppose there is no dark matter, right? Then the forcing term, all the gravity is coming from baryons, which are oscillating, right? Which means that the driving force is oscillating with the natural frequency of the oscillator. So it will enhance the amplitude of the oscillations greatly. We will see much, much higher oscillations, amplitude oscillations in the plasma in the absence of dark matter than you would already ordinarily see. Right, so if F is oscillating at a natural frequency, the driving force, it means that the amplitude increases greatly. So enhancement, it leads to enhancement. Amplitude of oscillations. And just because we don't see such high oscillations in the CMB, it tells you that actually not all of the matter can be baryons. You need some core dark matter. There's a very interesting actually essay by Dodelson. If you are interested, you can read it. I have the reference here. So you can see actually, this is the archive number. This is actually, I found a very nice argument against any of the Mond-like theories. Okay. Let us go a little bit further. In the 15 minutes which are left. So if this was all there was, then what we will see when you go from this Fourier space to L space, we will see the same features, which means the CLs that you will see, right, will be something like this. You will have oscillations. There will be some asymmetry between odd even peaks because of the presence of baryons. But in the end, the oscillations will actually go on like this for very high L, even at L of 3000. Let us say this is 3000. I am not counting the peaks, but it will go on and on. But this is not what we see actually. What we see, let us plot this in the log scale. So this is a log scale. What we see actually is that you have oscillations, but then they start dying down. They are very exponentially damped. So what is happening here? So until now, we are working in actually tight coupling limits. So we have only equations for monopole and dipole, right? But we expanded this difference between photon and baryon velocities only in first order in 1 over tau dot. But if we go to second order in tau dot, and there are additional effects, in particular, there are dissipation effects. And also so this term gives you dissipation at second order in 1 over tau dot, and also the quadrupole term. So this is coming from difference in photon and baryon velocity. This is in hydrodynamic terms, this is a thermal conduction term. The heat is getting conducted. And then a non-zero quadrupole. We assume quadrupole is 0 here. But if you say that quadrupole is not 0, you can again get analytic solutions. And the quadrupole actually introduces a shear viscosity. So viscosity and conduction, they dissipate the sound waves. But we can understand actually without solving these equations, we can understand the dissipation or most of the physics of dissipation without going into these Boltzmann equations. So what is happening here is, so in the early universe, you have this before recombination, you have sea of electrons, right? And photons are bouncing off these electrons. They are doing a random walk. So the mean free path, the tightly coupled limit means, or very high Thomson optical depth means, that this mean free path is very, very small for photons. So they can travel a very small amount until they're scattered again, and they're scattered again. And that is what is coupling the fluid and the photons. The distance which a particle can travel during doing a random walk depends on number of steps. So after n steps, you can actually, the electrons can actually traverse a distance, or photons can actually traverse a distance, which is of order square root of n times the lambda mean free path. There is actually a factor of 3 here because we are working in 3 dimensions. So n is actually, even though this is very small, this is very large, which means that the diffusion scale can be very, very large. And photons can diffuse. They cannot go travel in straight lines to very large distances. The free streaming length is just mean free path, but they can diffuse doing a random walk to quite large distances. If you look at some wave of scale which is diffusion scale, right? So You take the one plane wave, then at some point in space, the temperature is higher. At another point, the temperature is lower. And the photons from here are going towards each other and mixing together. So this is erasing the modes which are correspond to this diffusion scale. And what you get is actually a damping. So theta 0 goes to theta 0 times e to the minus let us see, k square over, let me make it clear. So the modes larger than the k modes larger than this damping scale are exponentially damped, and that is what we see here. So by looking at the CMB, you are actually also learning about the diffusion scale. And this diffusion scale depends on what is the number density of electrons, because that determines the free, lambda mean free path, and also the details of the recombination. So the information about this damping, how much damping you do, this gives you is information about cosmological parameters. But I don't want to do cosmological parameters with this physics. What I would now want to do is actually look this. We established that these photons, they dissipated, so the perturbations have gone away. Right? But what has happened to these photons which dissipated and mixed together? So they are now averaged out. So perturbation has averaged out. So this, all these photons are now part of the monopole, the average CMB background, right? And we can check what is happening to these photons. So each point, the photons have a black body spectrum. At each point in space, they have a black body spectrum with different temperature, right? And the diffusion is mixing these photons which have different black body temperatures. So we can write down the photon spectrum or the occupation number. Right? The Planck spectrum is given by e to the h nu over kb, and then each point has some different temperature, some difference from the average temperature. Right? This is a Planck spectrum. So what happens when you average that? What it's doing is it is just averaging. We are just averaging the photons with different temperature. We can actually do a Taylor series expansion of this and calculate this. So we want to calculate actually the average over all temperatures. This average is over distribution of temperatures which are mixing together. Actually, the easy way to do this temperature is actually not think in terms of T, but logarithm of T. We can actually write that as, let us call this Planck. This is a Planck spectrum. So average of Planck spectrum, let us write this as logarithm of average temperature. So T is average plus delta T. Right, so I've just taken T equal to T plus delta T, average T. I take out the average T, so this becomes 1 plus delta T over E bar, and then you take a logarithm of this, then this is logarithm of this term plus logarithm of this term. Right? And then we can do a Taylor expansion around this. Yeah. We do a Taylor expansion around this average temperature. So do a Taylor expansion of this function. What you get is a original function, Planck spectrum at average temperature. This is just a change of variables, nothing profound going on here. Instead of using T, I am using logarithm T as my variable. Plus, there is a first order term. There will be a term partial n Planck, partial log T, which will have a coefficient that is log of 1 plus delta t over t, that is our perturbation, plus 1/2 plus delta t over t square we expand up to the second order. Okay, yeah. And then there are higher order terms. We can expand the logarithm also. So we want to expand everything up to second order in delta t over t. So we can expand all logarithms also up to second order in delta t over t and keep only second order terms, which gives you, now just write it as n Planck of t, t bar plus delta t over t let us, we are taking the average, so this is, so now the average is only applied to the functions which are functions of that t over t. So this, so there was average here over temperature distribution. So we have this plus delta t over t square, its average, and this multiplying by the first term. This is t. The log t becomes t 1 over t. This is a partial n over partial log t. That is just t partial l, partial n partial t, plus a second order term, which is 1/2 t to the 4 again. You will, after doing some algebra, you can write everything as this. So these t's are all average t's now, right? Okay. So now the average of first order, first term, this vanishes. This is just 0 because we are fluctuating about the average t. So by definition, average of delta t is 0. This term, this is just a first order term. So up to second order, actually, we can just absorb this in this. So up to second order, this is equivalent to n Planck of t times 1 plus delta t over t whole square. These two terms. Because when you expand this, the difference between this and these two will be actually fourth order in delta t over t square. Plus, we have 1/2 average of this variance of the temperature times this term. Actually, you can recognize as Sonia-Zeldovich effect. I think maybe John Peacock or someone else covered the Sonia-Zeldovich effect. And this is actually exactly that formula. So if you expand this, you put in n Planck equal to 1 over e to the x minus 1, where x is h nu over kt, and do the derivatives. This actually turns out to be just, it's just the Sonia-Zeldovich solution, which in terms of x is just x e to the x over square x e to the x plus 1 . Okay, we started with CMB anisotropies, and we have arrived actually at the Sonia-Zeldovich effect, which I think in the cluster lectures on clusters, you will have heard a lot about it. So what is happening here? What is the relation between this mixing of black bodies and Sonia-Zeldovich effect? So it is actually not that difficult to understand. I think we started 10 minutes late, so we have 10 more minutes. So your coffee break will be shorter by 10 minutes. I hope you are okay with that. First, you note that actually the silt damping is giving you spectral distortion. It has distorted the spectrum of CMB. It has given a wide distortion to the spectrum. So by looking at the wide distortion, we can actually measure how much power there was that dissipated. It is a probe of looking at very, very small scales, because as you go to higher and higher L, the CMBs, these are getting exponentially suppressed. You cannot measure them directly. But by looking at the spectral distortions, we know actually how much power there was. It is a way to go to very, very high L. So Planck is going up to L of 3000, but with this you can actually go all the way up to L of 10 to the 6. I think in the Chandra lectures by Rashid, you will hear a lot about these things. Let me just give you a connection between Sonia-Zeldovich effect and what is happening here in the mixing of black bodies. So usually the Sonia-Zeldovich effect, you understand, you have some cluster which has fast-moving electrons, and background CMB photons come, scatter off, and they gain energy because they interacted with this high-energy photons. So they get some energy from the electrons, and the spectrum, so the black body spectrum actually moves. All the photons get energy, the spectrum moves to the right. Right? If this is frequency, all photons have some energy. And if you take the difference, you get this Sonia-Zeldovich spectrum, which the formula is given over there. So you have this, it passes through 0 around 217 gigahertz. We can also do actually same physics in the reference frame of electron. Because as long as we are dealing with the occupation numbers are Lorentz invariant. Right? Occupation numbers are the phase space density. It is the number of photons divided by phase space, which is d cube x, d cube p. And if you know special relativity, you understood your special relativity well, you should be able to prove if you do a Lorentz transformation, then these two terms transform in the opposite way. So this is invariant under Lorentz transformation, which means we can go to actually any frame instead of, so this we are doing in CMB rest frame. We can go to any rest frame and do this calculation. In particular, let us go to the rest frame of one of the electrons. So the electron was moving very fast. If you go to the rest frame of electron, what we will see is that when CMB was isotropic and electron was moving very fast, when you go to rest frame of electron, the CMB is now actually has a dipole. So if the original direction of CMB electron was this velocity, then from the point of electron, actually CMB has a higher temperature here and a lower temperature in the opposite direction, because it is moving towards CMB in this direction and moving away from the CMB here. So it is seeing a dipole. And the electron rest frame, what Thomson scattering is doing is that photons coming from here are going scattering in some other direction. It is just mixing the directions of these photons. As far as electron is concerned, this is just, it is seeing an anisotropic radiation field, and it tries to mix all the photons together. Scattering all mixes all these photons together. Which means that all the theory that we applied is applicable even here. In particular, the same formula should describe the spectrum of the photons after they have scattered on these electrons. And that is exactly what we get. Okay. I think 5 more. Sorry? I can take a few more minutes. So this is, I just wanted to, I think no one talked a lot about polarization. Did anyone discuss basics of CMB polarization yet? No. Just, I will give you just a qualitative understanding of where the CMB polarization is coming from, what are E modes and B modes. And so in the next lecture by Jens, it will tell you about the recombination. At some point, around redshift of 1000, Before redshift of 1000, the universe was ionized. You have electrons, protons in this simplistic picture of recombination. I think Jens will go into the gory details of what is happening here. But for me, it is just before that you have electrons, protons. After that, you have neutral hydrogen. Right? And this is called last scattering surface because photons are scattering here. But at some point, at last scattering surface, they just come straight to us. So they have scattered last time somewhere around this region, around redshift of 1000, before coming to us. And the scattering of photons actually can, if there is some anisotropy, there is some asymmetry, and there is asymmetry here, there is a lot of scattering here, no scatterings here, then you can actually create a polarized light from unpolarized light. So here all photons are unpolarized, because they are just bouncing around in different directions. Initial photons were unpolarized. The Thomson scattering is actually sensitive to polarization. It is a consequence of the fact that, you can think of it as a consequence of the fact that photons do not have any longitudinal polarization. Right? A linear polarization of the photon is going in some direction, and the polarization vectors are always orthogonal to the propagation direction. Right? If this is E, let us say E hat, this is direction of propagation N hat, they are always orthogonal. There is no longitudinal photon. Which means that, and the consequence of this is that the scattering cross-section is actually proportional to the Thomson cross-section, is proportional to the square of the incoming. So E is the, if let's say photon comes, one particular photon comes with a polarization E, and it scatters into in some direction into a polarization E prime. And the scattering of a polarization E into E prime is proportional to E dot E prime square. Which means in the orthogonal direction to this, you have no scattering. So let us see what happens in the last scattering surface. Let us take one plane wave. Right? Let us say 1K mode, which has some compression here. There is a sound wave, which you have compressions as this wave is, perturbation is entering. And you have fluid motion initially, as the perturbation is entering inside. There is a fluid motion towards the overdensity. Right? So the photons are moving in this direction towards the overdensity. This is looking at a mode which is entering the horizon, or a little bit before, at recombination, or a little bit before recombination. So the electron which is sitting here is actually seeing a higher temperature from photons, which they have a velocity towards this electron. It sees plus delta T here, plus delta T here. But here, there is no motion. We are looking at just one plane wave. So here it is just T. We have a quadrupole moment in temperature that the electron is seeing. So the photon, which is coming from here, let us say with the temperature delta T, it has, let us say this is the recombination surface, and photons are coming in this direction and then scattering towards us, and we are sitting here, the observers. So these are unpolarized photons. It will have, if you decompose into two polarizations, two linear polarizations, they will have equal amplitude for this photon, which is proportional to this delta T, T plus delta T, and slightly higher temperature. And these photons will come towards us, scattered by 90 degrees. Now this photon cannot scatter towards us, because if this photon scatters towards us, this polarization will be longitudinal. And it's just in cross-section, it is just coming as E dot E square. When E is orthogonal, the scattering is 0. So this photon cannot scatter here, only this photon will. Let me draw it a little better. They are coming towards us, so only this photon will scatter. We will see this photon only even with a temperature of T plus delta T. Now the photons which are coming from here, they have a polarization direction, let us call that E2 prime. And E1 prime. And these have a temperature only T. So in this case also, this E1 prime will not scatter here, because it is in the same direction, only E2 prime will be scattered. So what will we get here is E2 prime. So these are the temperature now T, but it came from a colder photons. So what we observe is actually there is a now difference between the two polarizations. What we will see is a net linear polarization. At the last scattering surface, because of the presence of a quadrupolar anisotropes, we get polarization. Now, if you remember your scalar vector tensor decomposition, so the polarization is actually like a vector field, but without any pointy arrows, right? Polarization you can draw on the sky as some vector fields, but there are no arrows now. Vectors have arrows, these have no arrows. But just like a vector field, if you remember from your scalar vector tensor decomposition, which Dimitri promised me he went into in great detail, this field also you can decompose into a curl-free part and a divergence-free part. And this curl-free part is actually called E mode. The curl-free part where del cross this polarization field, let us just call this P, is 0, is called the E mode. And the divergence-free part, which has only the curl component, is called the B mode. So actually, let us just call it curl-free, and this is divergence-free. So curl-free just means that this is a scalar. This is a scalar quantity, right? And this means that this is a purely vector quantity. This is a divergence-free. So scalar modes actually cannot create this, right? Scalar force, if you have only scalar modes in the universe, we will only have E modes. Because you cannot create a vector from a scalar. But if you have a vector perturbations or tensor perturbations, then they have actually a divergence-free, by definition, they have divergence-free components, so they will create a B modes. This is actually the importance of B modes and why everyone is after B modes. Because scalar modes are actually the biggest perturbations that are there in the universe, so they provide a big background. If you want to detect the signature of vector and tensor modes in the background of scalar modes, it is very, very difficult. The scalar modes actually provide the cosmic variance, and you cannot really measure anything better than the cosmic variance. But B modes, because scalar modes do not provide any B modes, and there are actually almost no vector modes as far as we know in the universe. This is actually a clean probe of tensor modes or the primordial gravitational waves, which is why everyone is after these B modes now. It's not exactly background free. Actually, the gravitational lensing converts some of the E modes to B modes because it can rotate the you change the this direction, structure of the field, the polarization field. But that is a small background, and we can predict because we know what are the scalar modes, the primary E modes. We know a measurement of structure, what is the gravitational lensing potential between us and the CMB. So in principle, this lensing background we can actually remove. A lot of work is going on that. And I think I will just stop here. Any questions? Everything was absolutely clear. Okay, then, thank you.